Yeah, hello guys, welcome back. It's me this time for a talk. So I will be talking about the black box in your data center, and I will start now. So shortly about me. So I'm a security engineer since over 15 years, I guess. I did a lot of stuff also for open source firmware development in the last 8 years. I'm a hacker from a hackerspace here in Bochum, Germany, and now I'm the CEO of Immune, which is a startup. And I also founded some conferences where you can just see there the logos and so on, and where I worked mostly for. The data center environment. So I will be talking about the data center and the problem of a black box in there. And the most data center devices are, I would say, from my experience, heterogeneous. There are some homogeneous landscapes out there. That means the devices are the same, but most of the time you have tons of different devices, different hardware vendors delivering those devices, and you have also different architectures in your data center. That means if you have switches, routers, firewalls, computing devices, or edge computing and more, you might have x86 systems, ARM 64-bit systems, RISC-V systems. That's really, it depends on what you buy there and from which vendor. And so thanks to COVID, the overall or the total DC data center growth quadrupled. So this is really insane. I just looked up the statistics a few days ago, and this is really crazy. So yeah. What can you control in your data center stack? So first of all, you have hardware, right? So this is, I guess, the most important thing, that you have hardware. You have some chassis, main motherboards, the components, the periphery, and more. This is, for example, an OCP data lake device, which is used by Facebook for computing. And aside from the hardware, you have software, which could be a bootloader, a hypervisor, operating system, applications, and more, right? I didn't list everything here, but basically software you have there. You can exchange hardware and software. This is not a problem at all, right? You can install whatever operating system you want and have a hypervisor or bootloader you want. And also you can get the hardware you want. But one of the main issues is that one thing you can change in your environment at the moment in the data center is the firmware. So the firmware is basically a black box, and that means it's probably possible to change it if you build your own hardware. But most of the time, you get the hardware delivered by some vendors, and it's really hard to change the firmware there, because it's signed, it's owned by some OEMs. And also, firmware is quite intransparent. And it's, let's say the last 30 years of firmware development, nothing spectacular happened in that time frame, and everything stayed the same. And so this world is quite, let's say, closed source, similar to the baseband area, or let's say the baseband ecosystem. And so, that's why I worked on that for the last 8 years. Yeah, how much do you really know about your firmware, right? So let's look at some hardware. So this is a Supermicro X11 SCH system, and you can believe it or not, but you have tons of firmware in it. So first of all, if you have PCI Express cards or PCI cards, they have PCI option ROMs, which are basically some kind of firmware for the PCI card, which is on the PCI card itself. On the Supermicro system, you also have an FPGA, and on the FPGA, it's quite funny. You can see that there's a red dot, and this red dot, or normally if there are dots on the chips, that means there's firmware on it. Aside from that, you may put a TPM on the mainboard with a header. Then you have TPM firmware. The Southbridge is there, so you have Southbridge firmware. You have the BIOS firmware, which is on some fancy, let's say, BIOS header. And the same goes for the BMC firmware. And so this is a lot of firmware, right? So if we look into firmware itself, today, or let's say in the next 10 years, I'm sure we get more and more processors and firmware components on main boards. That means if you have, for example, a modern laptop from Lenovo, ThinkPad, whatever version, it normally contains already multiple processors and firmware in it. And so the firmware is normally there to initialize the hardware components. and it's also used as root of trust, right? So if you do trusted computing, we normally trust the firmware because the core root of trust for measurement is inside the firmware itself. And also the firmware configures platform security technologies. This makes firmware quite, let's say, unique. And also it's the first part of code which is executed normally on a platform. Most of those firmware you find from vendors is bloated because a lot of vendors think that value add is quite important for that components, which is probably not orthogonal with IT security and the small TCB. And so it's so complex that you can see that. So on the right, there's some Twitter post from 2 days ago from Mark Ermolov. He's a security engineer, does offensive stuff. And he found out, for example, that there is some kind of, so there's a special mode called system management mode. And normally you shouldn't be able to unlock registers like the feature control register on Intel platforms, but it was possible to do that. So normally they are locked inside the BIOS, and afterwards you shouldn't be able to unlock it, but you could do that. And even the documentation from Intel wrote that this is impossible. That means even the SOC vendors, they have really huge trouble to control all their components in the stack. And if you have a modern Intel platform, you already got around 6 firmware components, which are running on 6 standalone processors. You can believe me or not, but this is the reality. And aside from that, a lot of vendors think that it really makes sense to layer security. So normally this is not a bad thing, right? If you layer security architectures over and over and over, but it makes the system quite complex. And so there is not really a small TCB anymore on those systems. The next problem with the firmware itself is the ownership story. So on the right, you can see the new PS5, right? This is just an example. So if you get a PS5, you buy the hardware, right? Normally you would say you own it, but the firmware and the components, also the software, which is not the case for the data center, but the firmware itself is also controlled by Sony. And Sony can shut off the PS5 or destroy it remotely. So that means you don't have control of your hardware, right? So, and the vendor is signing the firmware on your behalf, and you can't. So you might be able to request firmware updates with some features in it, but everything is configured. Even the security features, which are used then later in the operating system or hypervisor, are configured by the hardware vendor. So this is really a big problem, and you don't have control of your platform. And often everything is closed source, proprietary, no source access. This was also my experience, my last company I worked for. And this is really troublesome if you want to design let's say, a trustworthy system. Yeah, transparency is another problem in the firmware world. So there are a lot of NDAs. So there's also no good documentation, even if there are NDAs and you can access the documentation. Most of the time, the documentation is incomplete. So, and this is a big problem. So open source firmware is there, but it's a rarity. So it's hard to get on hardware platforms. So software supply chain is also hard to control because if you get the firmware, for example, you get a device from China, you don't know through how many hands the firmware moved and what is running on your system, right? So it's unclear. So, and also the platform features, they're there, but you don't know if they're really supported. So, and if they're really good configured so you can use it. For example, probably the BIOS tells you if Intel SGX is enabled, but it doesn't tell you if the flexible launch control feature is there. And so this is really a problem of transparency. So is this really real, or do I talk bullshit? So if we look at the firmware growth of the last 20 years, the firmware grew from 1 megabyte to 264 megabyte in the data center world. Probably even more, depending on the platform, or probably less, depending on the platform, but it's already a lot. And if we now just do a small calculation, like we say 1 million lines of code equals 1 megabyte in C and assembly language, and we have every 2,000 lines of code 1 bug, then we have in a modern platform like the Supermicro system around 128,000 software bugs. This is a lot in terms of security. Not all are exploitable for sure, but it's a really big issue. Also, Gartner, Forrester, and Microsoft were talking about this the last 2 years. So Microsoft is, I guess, the newest statement from them is that around 80% of the enterprises have experienced a firmware attack during the past 2 years. And this is really insane, right? So you probably don't believe it, but it's there. And I also heard that from our customers, from us, and they are hyperscaler. The impact of firmware attacks is really bad. So it's easy. First of all, it's quite easy to do supply chain attacks. Normally, you can say, okay, I need to do a hardware attack, but most of the time, if the system or the firmware isn't configured correctly, or the platform configuration misses burn fuses, you can just use a $30 device to flash new firmware on it. So you don't need to attack a hardware to do a supply chain attack. You can just rewrite the firmware with your own code in it. Aside from that, you have persistency. So if there's malware inside your firmware, how do you get rid of it? Yeah, and the other way around, how do you attack that? It's really hard to detect that. And so the support from the hardware vendors is not really good most of the time. Probably you are lucky and you have a good hardware vendor supporting you quite well. But my experience is bad, even after working the last 4 years for a firmware company developing firmware for. So it's really hard to get good support from them. Aside from that, you have misconfiguration from the hardware vendors itself. So they don't understand security. So don't believe hardware vendors are security experts in any kind, even not firmware security, not cryptographic knowledge, whatever kind of security knowledge, they don't have that. Probably some companies might deliver that with some experts in it, but most of the time they are not really experienced. Aside from that, you have update problems because the update availability goes away if the platform runs end of life. And also, how long do you wait for an update? You can't update the device yourself because it's signed, right? So how do you do that? And in let's say, if we look at that and say, if we had an attack, how high are the incident costs, right? They are really high because it could be that the platform is, let's say, it's hard to detect which platform was infected. You have to throw away the entire data center hardware, or you can figure out which hardware it is, but you can't remove it from the firmware because you don't have the techniques or technology to do that. So you have to throw away the hardware as well. And this is really, really, really dangerous and costs a lot of money. So what can we do in order to solve this problem and somehow, let's say, find a good way to circumvent that? So first of all, we can use open source firmware and system transparency. So we try to make system transparent as possible and have open source firmware on the machines. So if you look at pros, it's really good. You have full control, customization, easy debugging, all that kind of stuff. You can build your own security from the bottom of the stack, right up, and it works. It's cost efficient in the long run because the maintenance cost is also quite low. So the cons of it is the initial costs are high. You need to get firmware engineers or some companies for that, and probably they do not do good work. So it's kind of hard to get started. And it's only possible for companies who build their own hardware. Yeah, and this is not always the case. Examples for open source firmware are, for example, Core Boot, Linux Boot. We also have system transparency, which is basically a project consuming Core Boot and Linux Boot and trying to make systems more transparent with an, let's say, boot architecture behind it for security reasons. And there are also other possible solutions. So I know from a HPE ProLiant Alpha program, they ship open source firmware on their machines. Not everything is open source, but some components, and you can update those components yourself with your own built firmware through the baseband management controller. And so this is probably also interesting for you. This is something you could do. And then there's the Open Compute project, which is basically a project for hyperscalers. And those hyperscalers, they want to get rid of the hardware in a few years. And so they resell the hardware to some vendors called ITRenew and Sesame. And you can buy those hardware, and some of those hardware has open source firmware already on it. So you can make use of that by just buying, let's say, Google or Facebook data center hardware. This is one way how to do that. Yeah, aside from that, there's platform firmware resilience and platform root of trust. So basically what I mean by platform root of trust is chips like a TPM, platform firmware resilience is more, it's not like a chip like a TPM, it's more like OpenTitan and some other chips because it can do deep packet inspection on the buses. So it has different approaches to secure firmware. So the pros are basically all those technologies offer remote attestation. If you have a PFR, you might have deep packet inspection for the bus or the chip itself, where the firmware is stored on. And also for the TPMs or platform root of trust, we soon have those systems mandatory for Windows Server devices. And this is really great. The cons are difficult to utilize for companies smaller than big hyperscalers. This is true because if you want to use these technologies, you have to at least build your own chip, or probably you can buy it in the future, but I don't know any company selling OpenTitan chips yet, or any kind of other Microsoft Pluton chips and so on. So it's really, it's problematic, and those PFR solutions have a high integration effort. So I looked into the Intel PFR things. This is really complex. And also other problems like the use cases are not covered sometimes, so recovery is probably hard and so on. And also only some devices may support firmware at rest protection. So they support firmware at rest protection, but not firmware at runtime protection. So that depends if the devices can support that. Examples for those devices are Microsoft Pluton and Cerberus, Google Titan for sure, and Intel PFR. I know there are more, but I only listed few because it's getting too full. And for the platform root of trust, I just use the TPM virtualized in firmware or as normal physical device. Yeah, the third solution in order to somehow solve the problem of firmware security is to do firmware monitoring and analysis. So you can do that manually, somehow, probably automatically, use some kind of detection method which detects misconfiguration, let's say vulnerable versions of the firmware, or directly inspect the firmware and look if there's malware in it. It's really good for forensics and incident response because you can then say, okay, some components of the firmware probably are insecure. And this could be also done through a remote attestation and some kind of platform root of trust, but you can't do that so much in detail because the specification for measurement is really measurements in UEFI firmware, and modern, let's say, currently deployed firmware is really, really bad. So this is, yeah, my experience from the last 8 years, let's say, working in that area. So you get then the final real virus scanner for the firmware, which is kind of fun. The cons are only few automated solutions are out there, and it requires higher privileges in the operating system, and you need to somehow get firmware dumps, which is also quite hard from the operating system point of view, and you need to have skilled engineers which have NDA access and so on. At the SOC vendors is really complicated. And without any additional PFR or platform root of trust, it's not trustable, right? Because you get the input from untrusted sources, so you don't know if it's really trustworthy. So this is why it's important to use some kind of additional technology for yeah, let's say, protection of that solution. Oh, sorry, that was too far. Examples for this firmware monitoring is, for example, Padsec. You can do runtime analysis on a system. For static analysis, there's a Converge security suite. The Christian talked about it. EDA Pro for sure. There's also a UEFI tool, and I think there are much more. Let's say, tools you can use to do that. Padsec is, I guess, the most common or well-known for x86 systems, at least. Yeah, what do you, so I talked a lot of about all the things. So what do we do at Immune in terms of solving this problem? So that's that's what we basically do. So we created a data center monitoring solution which combines remote attestation, so identity and integrity protection, and firmware monitoring together in one solution. And additionally to that, we give the customers a platform insight. That means we gather information about the platform security features and check if everything is correctly configured in the BIOS and so on. So this is what we do. And then if there's some kind of let's say, incident, or we think there might be an attack, we give some feedback to the customers and let them know what could probably happen, and if that's really an attack or more like Iron said, if it's something you expected because an update happened or whatever. Our solution combines, as I said already, remote session and firmware monitoring. Interestingly, it's a SaaS, so software as a service. It's GDPR compliant. You install some client tool on the targeted server you want to protect, and we support Linux and Windows support, and it's open source. It's not out yet, but it will come out soon. So we have everything ready, but we're doing internal testing, and we hope that before the end of year appears, we make it public, and then you can, in theory, use that to protect your own servers, for example, or just play with it around and see how that works.